In the last session, we are discussing about various design rules of solar cells, right? So we have discussed about utilization of band gap, spectral utilization, light management, right? And yeah, all these things we discussed, right? Now we'll see for the most popular solar cell, right? This crystalline silicon solar cell. So for this crystalline silicon solar cell, how do you, design and maintain all these, rules, right? So that we'll see today. So in this, as I have just put a two solar panels right here, there. One is little bluish, uh, and other one is dark in color, right? So can you tell, someone can tell me the difference between these two panels? Any idea? If you see carefully, zoom little bit more. Now maybe little bit, anything you can guess from this image? Anyone can guess?
Sir, the construction of individual solar cell in the entire panel is looking different, sir.
Okay, individual solar cell construction looks different. Okay, anything?
And the dark one, it might absorb more light than reflecting. The light one might reflect off more light.
Right, the blue one will reflect back more light. That's why it is bluish, right? Blue one, it is reflecting basically. But dark one, it is
Yes.
absorbing everything in the visible region, right? So which one is preferable? Of course, this one, right? The black one. The solar cell ideally it should look black. But this one, if you see carefully, the texturing and all, there are some kind of, different shades you can see, right? So basically, crystalline silicon, it comes, silicon solar cell, it comes two different forms, right? One is polycrystalline and single crystalline. So which one do you think is single crystalline out of these two?
Sir, I think the black one is single crystalline, sir.
Exactly. So this one is single crystalline, and blue one is polycrystalline because you can see the major reflection which is coming here from the grain boundaries, right? You have come across different types of material, right? Single crystalline material and polycrystalline material. So polycrystalline material will have, it is made up with very tiny single crystals, right? That's why the name called polycrystalline, right? So it is made of multiple single crystal material, and each single crystal, each one of them will have grain boundaries, right? And grain boundaries will generally, there will be some scattering of light in the grain boundaries because there will be sudden abrupt change in the crystal orientation at the boundary. So refractive index will change at the boundary, right? And there will be scattering phenomenon from this kind of polycrystalline material. And that's why you see here it is little bluish, and this panel is polycrystalline. And if you see carefully, one more observation here, this single crystalline, each cell one. So I'll just draw one. Uh, take this green one. So each cell you can see there is a cut, right? And they are not perfect rectangle here. You can see there is a cut here, right? But whereas in the polycrystalline one, you can see they're perfect square, right? Or perfect rectangle, whatever. There is no cut in the corner, this portion. So any idea why so? No? Okay. In polycrystalline material, when you talk polycrystalline material, is there any preferred orientation of such kind? Nothing, right? Polycrystalline, they are those crystal or the grains, they are oriented in any direction, right? Randomly they are oriented, right? So that's why when you make this kind of polycrystalline wafer or sheet, we don't need to cut them in a preferred direction, right? You can cut in any direction because these grains are randomly oriented. But whereas in single crystal, there is a preferred, there is a particular orientation, growth orientation, right? Because the single crystals, they are grown by Zogralski, right? So you get this kind of big ingot, right? You remember? And then from the ingot, we slice them off, right? Roughly, I'm just drawing it. So while slicing it to make this, the to mark those, which direction it has grown and which direction we are going to cut. So we generally prefer to chop or cut off one of the sides. Okay, so that's where in each single crystal silicon you will see a mark for this orientation. These are kind of, we are marking that which direction the crystal is grown. Okay, so it's an orientation mark. And yeah, so you got the color difference in polycrystalline. It's because of the diffuse reflection, right? The scattering phenomenon from the grains, right? So whenever you buy or prefer going to buy a single solar cell, look at the color, and then you can easily say that which is single crystalline or polycrystalline panel. Of course, this single crystalline panel will give us much better efficiency. If you see commercial one, the single crystal panels, roughly it gives 15 to 21% of efficiency, whereas this polycrystalline one will give us efficiency roughly 12 to 16, in that range, roughly. So obviously, this crystalline one gives better efficiency, and cost wise also this is little costlier, roughly 20% will be costlier, this single crystalline panel. Okay, now coming to much deeper inside, that how we are making this solar cell, right? The designing, why we design in this fashion, right? Why not some other shape and size, right? So we'll try to understand that. Or each cell, what is this bus bar, we discussed already. Here the other one, what is called bus bar, and this fins, these are not seen here, but ideally there are fins here, right? You are not seen in this diagram, just a schematic. Okay, so we'll see that what is the what should be the thickness of this, what should be the distance between these fins, and how thick is this each cell, right? There is a definite thickness of this cell, right? So how can you determine all this, we'll see now. Okay, yeah, so to start with, how we grow this for the single crystalline panel, how we get this wafer, this technique we already know, right? Czochralski process. So I'm not going to the detailed of this because we discussed earlier this full mechanism, right? Please go through that that portion, that class, or you can even read it from our textbook. I'm not going to repeat this one unless it will take time, but you know all this process, right? All these steps we already learned. So we take it from here. We are getting the silicon wafer, right? So and I'll share one nice few videos to look at this process so that you can visualize the different steps. Okay, so we have the silicon wafer first. Now, when you make these wafers for particularly solar cell application, what we do is, while growing this, let's say here we are going the Czochralski technique, right? We are growing the single crystal here, right? So we don't grow just pure N type, pure silicon. This is the ingot, right? We don't grow pure silicon single crystal solar. We don't grow pure silicon single crystal. So while growing itself, we add p-type impurity in it, right? So p-type is like trivalent atoms, right? So we drop them in this molten silicon. We add those trivalent atoms here itself. Okay, so whatever it is grown for the application of solar cell, right? While growing itself, we grow it as p-type crystalline silicon. Okay, so we write as C silicon. C silicon means crystalline silicon. We grow like that. So after swaying, this wafer is already p-type. Okay, now swaying, while swaying, what should be the thickness, right? Typical thickness. So that thickness is again determined by the design rule earlier we saw, right? So from the Beer-Lambert's law, we find out that what is the typical thickness required to absorb at least 90% of the photons, right? So if you calculate, then it comes roughly around 230 nanometers. You can use Beer-Lambert's law, take the absorption coefficient alpha values for typically we target for photons wavelength up to 900 nanometers. Okay, not below that. Below that we don't take, because if you want to absorb below this wavelength, I mean much lower photons, then we need very thick wafers, right, which is not economically viable. And not only that, if you go for very thick, then there will be problem with the high energetic photons, right, that we have seen earlier, right? You have to see the generation rate and recombination, sorry, generation rate and collection rate. This multiplication we have to optimize, right? So we target up to wavelength of, I mean, 900 nanometers. And if you consider this wavelength lambda of 900 nanometer, and if you see the absorption coefficient of silicon at 900 nanometer, I am not going to the numbers. You can always get it from the absorption. We already discussed last class the absorption coefficient curves. So from there you can get these values. And now from Beer-Lambert's law, right? I equals to I0 e to the power minus alpha t, right? So this I by I0, we are taking 90%, right? So it is 0.9, 0.9 should be e to the power minus alpha t, right? So alpha you will get it from the curve, the absorption curve, right? And then you can easily find out the required thickness for this silicon wafer. So it comes roughly around in this range. Okay, so typical solar cell thickness, that's why we prefer this 150 to 250 nanometer in this range. Okay, roughly we can tell that 200 nanometer is the typical wafer thickness here. Okay, but it can vary depending on the the optical design we are doing, the surface structuring we are doing on the top. So it will depend, but roughly in this range. Okay, so we know right now how, while swaying, that what should be the each wafer thickness. We get it from this light management rule. Okay, it's not randomly we are doing it. So this is fixed. Now then then it comes that we need to create the junction, right? So we have now just the p-type wafer, right? So if I draw it here side by side, one. So you will get a circular disc only, but for solar cell application, we generally prefer this square shape, right? Because we need to make a panel out of it, which is rectangular in shape, right? So we cut them into this kind of rectangular shape or square shape, depending on usually it is square shape. Okay, now now let's say we have this p-type wafer. Okay, so we have the p-type wafer. This is just p-type, but we need to create the junction, right? So what you do is we have to create the n-type layer, right, on top of it. So on top of it, we do ion implantation, right? We know that how we make. So there are two types, and two types of barriers we can get, right? Step graded and what are those two types of junctions? PN junction we studied in the last semester, abrupt junction, and what is the other one?
Linearly graded.
Linearly graded junction, right? So for this PN junction or this solar cell, we'll choose one of them, and then yeah, so depending on how we are doing this ion implantation, right, a high energetic or low energetic ion implantation, we create this junction here. Now what should be the typical thickness of this n-type layer, right? So that we have to define, right, this n-type layer. How thick or how deep we should dope, right? That also matters, right? So that is again determined by, if you see the the generation rate curve with thickness, right here. So the photons fall on this surface, right, and the generation rate is highest on the surface, and as it goes inside, the generation rate keeps dropping, right? So from there we determine that what should be the n-type layer thickness. Okay, so typically the n-type this layer thickness is roughly 0.3 micrometer, right? So you can imagine that whole thickness, whole wafer thickness itself is 200 micrometer. Comparatively, the end layer thickness, the top layer end layer thickness is very less, right? It is just 0.3 micrometer, kind of 1%, right? Little more than 1%. Or no, it's even less than 1%, right? 0.3 by 200 if you do, it's less than 1%. So it's very, very thin, right? And why we are doing that? So for that understanding, you have to see the generation curve. So if you see the generation rate, so generation rate means EHP generation rate, okay? EHP generation rate, which has unit of per unit volume per unit second. Okay, so at the surface now let's define. So y-axis we have the generation rate, and x-axis we have the depth. Okay, depth of the cell. So on the surface, on the top surface here, okay, on the here the generation rate is maximum. Typically for, if you take silicon solar cell, crystalline silicon solar cell, and if you use M 1.5, the standard radiation, then you will roughly get 10 to the power 20, the maximum generation rate. I mean 10 to the power 20 per cc per second. So that means when we sign the crystalline silicon solar cell with M 1.5 spectrum, it is generating 10 to the power 20 electron and hole pairs per unit centimeter square, I mean per unit cc, right? Per unit cc, how much? It is like if you take a cube, just for your imagination, so it's each side is 1 centimeter, right? If you take a cube like this, so this much volume, 1 centimeter, 1 centimeter, and depth also 1 centimeter. In this volume, it is producing 10 to the power 20 electron and hole pairs. It's huge, right? Per unit second. Now this is on the top surface. Okay, so as the photons enters into the surface, so they are generating EHP, mean they're getting absorbed, right? So the photon flux density will reduce, generation rate also will reduce as we go inside the solar cell, right, from the top. So the curve looks something like this. It falls very drastically at the surface, and it goes something like this. Okay, so it's 10 to the power 20, and then it reduces to 18, 16, 14, 10 to the power, right? 14, 10 to the power 12, and so on. But this scale, it is in log scale. Okay, this scale is in log scale. And then typically when you go to roughly, if you go to 300 or 300 micrometer, the generation rate drops drastically. So we don't have high generation rate at the back when you reach the other side of the panel, right here. So that's where you determine the also what should be the typical thickness of the solar cell, right? So this is 300, this may be 100, 200, right, micrometer, right? And if you see on the top surface, so this is the top surface, right? And this is the bottom surface here, right? At the top surface, and maybe somewhere here or even less, right? To put in scale, here will be our junction, right? So this side we have the N type and rest is the P type on the right side, right? And typically it is seen that if you take the N-type thickness about this 0.3 micrometer, we get the best, efficiency possible. Now, if you see the real cell structure, it's not just P-type and N-type, we already know, right? So just let's connect this figure once again. So this is, so in this, the total cell thickness itself 200 micrometer. So wafer thickness will be much lesser in this case because it includes the back contacts, it includes the front contacts, it includes anti-reflection coatings, right, all together. So maybe the wafer itself just 150 micrometer or so. Anti-reflection coating thickness, roughly it is in nanometer. So these are not in scale, okay? This diagram, the schematic is not on the scale. Because as you can see, this P-type wafer thickness is this much. Comparatively the N-type, so yellow one is N-type or N plus, here it's written. So I'll come to that why we go for heavy doped. I'll come to that, but let's consider this is our N type, or this is also known as emitter of the solar cell, right? And if you see comparatively this thickness, it's not in scale, right? Ideally this N type emitter thickness will be much lower, and the anti-reflection coating thickness also here it looks very high, but anti-reflection coating typical thickness is roughly 60 nanometers and so on. We will calculate this and see, okay, later. But what I mean is, don't go by the dimension is mentioned here, right? Back contact thickness, you see, it's too high, it is kept here, but ideally it will be few, again, micrometer only, or even nanometer also fine, because these are metal electrodes, right? So the thickness are not in scale. Okay, now what do we have? So we have the P-type wafer here, right? And then we have N-type layer. So yellow one is N-type layer, and then we create one N plus, just top of the N-type layer we create N plus, okay? I mean N plus between the metal and N-type. So let's just try to understand this once. So we have N, P, and before the metal we make this layer N plus, okay? So N plus is here, and then we have the metal, okay? This is metal. So similarly for the P type, we make here one P plus, and then we put the metal contact, okay? And yes, we have anti-reflection coating in between, I mean in between the metal on top of the metal only, generally the anti-reflection coating it is. Here it is not clear because this anti-reflection coating should not be on top of N-type, right? Because anti-reflection coating generally they are insulators, right? So but sometime what happens is the anti-reflection coating we choose such a way that it will act as both. One is surface specification and anti-reflection together. Like for example, silicon, if you consider. So in case of, let me just go a little bit right side, because in the light management, we need to take care of the reflection coefficient, right? So for silicon, ideally we use silicon oxide, so it is SiOx. So depending on the oxidation state, we just putting is in general X, but silicon oxide is the most stable one. Okay, so silicon oxide on top of this N-type layer, this anti-reflection coating, it could be just the silicon oxide, a thin layer of silicon oxide, or we can use it silicon nitride also. Okay, SiXNY. So depending on the again oxidation state, it could vary. Okay, so these two, why we are discussing this, these are anti reflection coating, or they are also act as a surface precipitation layer. Both they can work together. Okay. For silicon solar cell, we generally prefer the silicon nitride because it has got refractive index of 2.1, so which is good for anti-reflection coating. If you calculate, the refractive index comes around 2.1, and this also acts as a surface precipitation layer because we need to minimize the recombinations, right? So if you consider crystalline silicon solar cell, so what are the different recombinations we have? So I'll just go on the right. So what are the different types of recombination we can have? Say crystalline silicon solar cell. So what type of material it is? Silicon? Direct or indirect? Anyone?
Indirect, sir.
It is indirect, right? Yeah. So in indirect bandgap semiconductor, what type of recombinations are more prominent?
Auger.
Yes, auger, and what else? And on the surface of the crystalline silicon, so one more before getting into the other type, I'll just tell a few information. Like in crystalline silicon solar cell, there is does it have any defects? It's a crystalline, right? Perfectly crystalline solar cell. I mean, perfect single crystal, let's say. So inside the bulk, the chances of defects will be much lower, right? But the surface where we are cutting it, right, sawing it off, or on the top of the wafer, right here, there is surface dangling bonds, right? So there are surface those dangling bonds, and because of that there are defects, right? That we cannot avoid. Even in single crystal also the surfaces are full of defects, right? Because of this dangling bonds present on the surface. Now, whenever we have this kind of defects, which recombination takes place more? SRH, right? It's a defect assisted recombination, right? So we need to minimize both this auger and SRH. So that's where we use this the remedy is surface passivation layer. And as I said here, the silicon nitride is better because this refractive index matches with the anti-reflection coating, like we already know, right? How to calculate the refractive index of anti-reflection coating. That is NARC is square root of N0 and NSI, right? So it comes roughly air 1, silicon is how much? 4.1, right? 4.2 or similar, right? Roughly 4.2. So it comes around 2.1. This refractive index of silicon nitride also, it is 2.1. So the silicon nitride, it works both. Okay, one is your anti-reflection coating as well as surface passivation layer, right? So silicon nitride, if it is there on the top, then it is precipitating the surface, and the surface defects are less now. And on top of this silicon nitride, we put the metal electrode. Okay, so we need to control this thickness also. Now thickness of this ARC also, we choose it such a way that that the most of the light it can enter inside. So there is again calculation behind what is the what should be the thickness of ARC, right? Okay, so we'll just finish up that discussion also, thickness of the ARC, right? So for that we need to understand this concept. So let's say this is the N-type silicon. Okay, and of course we have the P-type below, right? On top of it we are putting this one is our ARC, anti-reflection coating, right? So the way we I mean the idea behind this, we're trying to now understand what should be the thickness of the ARC, right? This X. We know the refractive index of the ARC we calculate from here, right? Because light is coming out from the air and getting inside the silicon. So the typical best thickness, best refractive index is square root of this, right? Now, what should be the thickness? Not only refractive index, right? So that is determined by interference technique again. So we let me just draw the ray diagram, then it will be clear. So let's say the light is falling on this ARC, right? So some part will get reflected back from here, some part will get transmitted, and this light also will get reflected from this. So first reflection is this is N0, let's say, this is NARC, this is NSI, right? So there are two interfaces, air anti-reflection coating and anti-reflection coating to the silicon, right? So there are two interfaces, so there will be two different reflections, right? Now we choose this thickness such a way that these two reflected beam interfere destructively. Okay, so if they interfere destructively, that means there is no reflected light as such. So all the light will be transmitted into the device, into the solar cell. So how can you do that? These two waves will so I am drawing here ray diagram, but if you draw typical wave of light, right, this, right, so they are basically interfering, right? These two wave will interfere. Now for a destructive interference, this phase difference light, let's say this is R1 and R2. The phase difference between these two, phi R1 minus phi R2, how much it should be? Anyone? For destructive interference, what should be the phase difference between these two?
5/2.
Close but not correct. For destructive interference. For constructive interference, how much? They should be
0, sir. 0.
right. So they should be in phase 0, and out of phase mean destructive interference, right? So out of phase, when do you say pi or sorry, pi/2 or pi? Pi, right? So this phase difference, when it is pi, then they will have a destructive interference, right? And for that to happen, this thickness should be how much? Anyone? This has to be a quarter wave plate, right? It should be λ/4 thickness, right? So for this λ/4, there will be a I mean, if you calculate optical path and all, there will be phase difference of pi/2, and because of, and also these two reflections, there will be phase difference of pi/2 in these two reflections. So at the end, we'll have pi/2 and here pi/2. So total pi phase difference, it will come between these two. So the thickness of this ARC has to be λ/4, or it has to be a we call as quarter wave plate, okay, in this thickness. So which has got thickness of λ/4, and this lambda is lambda in this ARC, right? So it will be λ0 over n, right? λ0 is the wavelength in the free space, right? So λ0 by n is the wavelength inside the ARC or inside this anti-reflection coating, right? So from here you can calculate. Now for typically, if you take a 500 nanometer wavelength, then you know, right? 500 by 2.1 into 4 nanometer. So if you calculate this, you'll roughly get around 60 nanometer, right? So we know the ARC thickness here by doing this math. So this is fixed now. So we are looking at this design. So ARC is fixed. Okay. So what kind of material? It could be silicon oxide. If it is silicon oxide, so let's finish that portion as well. So how can you make this, right? Silicon oxide, it's very easy. If you are going with silicon oxide, then if you take the silicon wafer and just heat it, okay, heat it with oxygen atmosphere, then this some of the silicon, I mean the top layer of the silicon wafer, it will get oxidized and it will form silicon oxide layer on top of the wafer. Got it? So the wafer itself, you just put it inside a oven, and yeah, there is a specific temperature and duration, because this thickness has to be controlled, right? We cannot grow very thick, right? So you have seen that roughly it is 60 nanometer, right? So to grow that typical thickness, we need to use a particular temperature and duration, and also oxygen, this oxygen atmosphere, the concentration of oxygen also matters, right? So all these things, they optimize in industry scale. So we take the wafer, keep inside the oven with a preheated preset temperature, keep it for, let's say, 1 minute or so at a particular oxygen concentration. Then you will get typical thickness of 60 nanometer, right, in this range. It's very easy, but we need to monitor it. If you grow it too much, then it will act as an insulator, right? Because the electron, whatever it is produced, right, it has to pass through this layer, and then only we have the metal contacts, right? So it will be again barrier. So we have to have a good control on this thickness, right? And for silicon nitride, it is a little difficult, not difficult. I mean, we use a technique called plasma enhanced CVD. Plasma enhanced CVD. CVD is chemical vapor deposition. So these techniques we'll be learning at the end of this course. Few of the thin film deposition. So this is one of the thin film deposition technique where we use to grow this silicon nitride layer on top of the silicon, right? Which acts as both anti-reflection coating and precipitation layer. So we'll learn this techniques as well, this thin film deposition technique. So it's a little complicated, unlike the silicon oxide simply hit in oxygen atmosphere, but here you have to go through this plasma enhanced chemical vapor deposition techniques. Okay, so we have the ARC now, and then what else? Now coming to the top contact, right? This metal contacts, right, on the top. So that we discussed earlier, we'll just very quickly brush through again. But one more concept is there, as you can see here, that we are using N plus type emitter. Okay, so we have N type, this one, this 0.3 micron, the N type layer, we have it here, right? But before the metal we put on top, just below the metal, we make the semiconductor where we dope it as N plus type. So why we are doing that N plus type? Because if you make N plus, then the metal semiconductor, we already studied the metal semiconductor junction behavior, right? There is a step, right, in the band diagram, right? So when the electrons has to go from the semiconductor to the metal, it has to overcome this Schottky barrier, right? Now again, depending on the metal and semiconductor work function, this Schottky barrier height can be tuned, right, towards ohmic, right? We want ohmic here. Yes. But if you go for N plus or highly doped N type, then the barrier height we can reduce significantly. The metal and semiconductor, the junction barrier height, we can reduce significantly. So it will be more ohmic in nature or less resistive. Okay. Now there is one problem. If you dope with N plus or very heavily N type, then let me explain that concept, that why we cannot dope N plus throughout the N layer. Why we are doping only just below the metal, right? So that concept we can easily understood by, let me just draw one schematic here. Or I'll go right. Okay, so now we are trying to understand that, okay, we have N type, we have P type. I'm just drawing a side view, and on top we are we'll be putting the metal, right? So this is our metal. I am now not drawing all this anti-reflection coating and all, it is there, right, in between, but we are here we are neglecting it, just to understand that how these electrons and holes can be separated or collected efficiently, right? So in this, when lights falls in, right, so it will produce electron and holes, right? Now if you make this N type N plus or N plus plus, heavily doped N type, right, whole region, then what happens is, here we'll have lots of electrons, right, lots of electrons in this region. One way why we are doing N double plus, because we want to reduce the barrier height between metal and the semiconductor, right? So we want to make it more ohmic in nature, or sorry, more conductive, less resistive. So we want to reduce the Schottky barrier height between this metal and semiconductor. That's why we're going for N double plus. Now what it will impact is, so if you dope very heavily, then we have already many electrons here, right, which are not photogenerated, which are because of the doping we have already lot of electrons, right, which I am drawing as green. So these are the electrons, thermally generated electrons for N double plus, right, because of the doping, heavy doping, we have, right, more electrons. And these black dots I'm putting, these are thermally this photogenerated EHPs, right. Now these electrons are already there inside, fine, this photogenerated electrons, but this hole has to travel towards the p side, right. You have to collect them, right. Again, if you draw a little more detailed, so we have here the barrier width, or let's say this is our active region, total active region is this one. So these holes, photogenerated hole has to enter into this active region at least, right. Then we have the this built-in electric field, it will be collected towards the p region, but it has to diffuse and enter, right. So the problem is, as we are making it in double plus or heavily doped, then there is already more number of thermally generated electrons present here. So these electrons can recombine with these holes, right, this thermally generated, right, and if it recombines with this hole, then this hole is lost, right. So it cannot take part in our photogeneration. So we cannot enormously, or we cannot just because we want to reduce this metal semiconductor barrier height, we cannot simply increase the doping concentration. Then we are losing holes, because now the diffusion length of hole is LH, it will reduce, right. Effective diffusion length of holes will reduce as we increase this doping concentration, right. So N is our acceptors, right. Acceptors or donors. N type, let's get confused. So N type mean we'll get electrons extra, right. So these are donors atom, right. So as we increase ND, not Na, don't get confused. So ND, donors atoms concentration, if you increase, the effective hole diffusion length is decreasing. So that means our effective, the solar cell area will reduce, right. We know the effective solar cell area is LH plus Ln plus the typical depletion width, right. So this will reduce, or in other words, we cannot collect the holes which are generated near the surface. Maybe we can collect the holes which are here, they can diffuse, but the surface holes, holes which is generated near the surface, they will recombine very easily with the electrons present in the N-type semiconductor, right, when you dope heavily. So you are reducing the cell efficiency by doing it. But one way is we can collect these electrons easily. So one way it is increasing, another way decreasing. So there is a trade-off between this, this increment of donor or the doping concentration of N-type. But in practice, to avoid this, what we do is, now we'll just go for a three-dimensional image to understand this. So we don't put the metal throughout the top, right? So we just put a strip here. I'm just drawing one strip on top. So this is just the metal, right? Or if you, this is the metal, and this is our N-type. Okay, we're just drawing the top. N-type is here, right? Now what we can do is, we have the junction between metal and semiconductor here, right? Just below the metal. So what we do is, just below the metal, right? Where we'll later, because this metal later it is screen printed, right? So we can mask this whole wafer, and then we can dope heavily only this region where we'll be putting the electrode later, right? So only this below region we can make it N plus or N plus plus, but rest other region, here it is here it is N type, or other region is N type, but just below the metal, the semiconductor, we can make it N plus or heavy dope. So here only the electrons will be collected through the metal, and then this electron goes to the back contact, right? So you understood this concept. Hope it is clear, right? Any doubts here? We'll stop today here. Next we'll continue. We have few more concept how we design the back contacts as well. No doubts, we'll stop then.